So we live in this data-rich world, okay? So data-rich world, and what we're trying to accomplish through this, especially in the 2 days here, the focus has been on data for good, okay? Getting good results out of this. And I was saying to someone during the break earlier today that there's this large retail store in the U.S. and maybe even beyond the U.S. You may have heard of it called Sears. And Sears has three product lines for their products. When you go into the store, you can buy good, better, or best. Okay, so they don't have anything less than good in their store. But that's sort of like where you start. So if you want to buy the low-end product, you buy the good. If you want to get a little bit better product line in whatever the thing you're purchasing, you can get the better. And then the highest end branding they have for products in their store is best. All right, so I like to just challenge us to think about not only data for good, but data for better and in data for best. Okay, so that's all I'm going to say on that, but I just sort of like to think about that. So today, the theme for me is this sort of data-rich part of this, okay, sort of the sensors everywhere. And sensors everywhere need some value proposition, and we're not just collecting data for its own sake. And sometimes you might think, well, of course we're not doing that. But I worked 18 years in NASA, and we always collected data to make those data publicly available to the science research community to do science. But the ways we made those data available in those days were not very transparent. So if you knew the index number of a data set, for example, AJH215-64A, then you could find it. But if you didn't know that was the index number of your data set, you would never find it. Well, I have no idea what that index number means. And no one else would know what that means. So what we did to make it more easy for people is every year at our data center we published a book which was about several centimeters thick. This book contained information, metadata, about 15,000 different experimental data sets that we had in numerical order by that index number. And we made 40,000 copies of this book every year and sent it to all the libraries and science universities around the world. Okay. So unless you can make your data useful and in useful contexts and in useful ways, it's not useful. Okay, unless you can do something with this fire hose of data that we're experiencing in our data-rich world that our sensors are collecting everywhere, then we can't achieve the good, better, and best from our data. So the amount of time I have, which I think it says in the program, just before my talk in the program, it says 17H, and I think that means I have 17 hours to talk, which is perfect, because my airplane leaves 17 hours from right now. So I will finish this talk via Skype in the taxi on the way to the airport tomorrow morning. But no, seriously, if we're going to discuss this, we need a whole conference, and that's what we've been doing here for the last day, and there were some discussions even among some of us yesterday. So it's not possible for me to cover a lot of things, so I want to cover just a few things in a particular context. And so I'll stand back in case that's blocking anything, so you can see that I'm going to go through a few topics here. They're all very short, so it's not 17 hours, believe me. Okay, so the key thing in all of this is bullet number 3, really. Sort of the core of the presentation is what I call the self-driving enterprise. Now, I'll leave that a little bit to your imagination, but think about self-driving cars and think about how a self-driving car might operate. That is, in terms of sensing its environment. There's sensors that are collecting data, and it enables good decisions, better decisions, best decisions to avoid accidents, that is failures in your business or your enterprise or whatever it is, and actually achieve the best outcome. So ideally, the self-driving car gets you more effectively, efficiently, and quickly to your destination with minimal safety hazards and minimal problems. All right, so we would like to achieve all of our business goals in the same way. We like to achieve all those goals with whatever stakeholders we have. So if we're in the medical profession, stakeholders might be our patients. If you're in the retail or commercial business, it might be your customers. If you're in the astronomy business like me, it might be asteroid tracking. And if we see an asteroid coming toward Earth and it's going to wipe out civilization, I think we need to do a little bit more than just tell you, hey, next Tuesday an asteroid is going to wipe out civilization. Have a nice day. Wait, come back. Okay. Same thing with your doctor. If you go to your doctor and the doctor predicts you're going to die of some cancer or horrible disease, and then he says, thank you very much, have a nice day, I'll send you my bill. No, I want you to do something to prevent this bad outcome. Okay, so what I am proposing here is that we use this fire hose of data, these streaming data, these sensors which are everywhere, and those sensors include social media, as we just heard in those wonderful presentations from the Dengue hack. A lot of those presentations, if I'm not mistaken, all of those presentations were using social media data. I just read Fritz's mind using his Twitter feed. So data comes from many different kinds of sensors. Okay, so it's not just like a scientific sensor attached to some device. It's also social media. It's the news. It's anything that is delivering data to our algorithms. So let's focus on this first thing. First came data, then came big data, and then smart data. What do I mean by that? So as humans, we're naturally curious. Okay, so I was telling someone earlier today that when I look for data scientists, I don't look for someone who knows R or Python. If a junior data scientist or an aspiring data scientist ever asks me the question, should I learn R or Python? My answer is yes. But what I look for is a person who has the passion and the curiosity for discovery, to learn how things work, and to not be satisfied when you get an answer, to challenge your own answers, to don't say, okay, I've solved this problem, let me move on to the next one. I mean, that is the wrong way to approach anything, because you have to have some humility before this, especially with the flood of data we have. You couldn't possibly know every possible thing you could know about something, because now we're tracking more aspects of every entity on planet Earth than we ever did. So someone also asked me once, how do you define big data? And there's a definition of big data in Wikipedia, which I'm not going to repeat to you, but I think it's ridiculous. Because using that definition, it basically implies that the ancient Romans had big data. Because the first time they did a census of the world and they counted how many people were in all their different cities and towns and villages and city-states, that was more data than they had ever collected before. So that was big data by the Wikipedia definition. But I think we could all write those numbers down on a single sheet of paper and probably before I even finish talking. So I don't consider that big data. So what I define big data is as everything quantified and tracked. We are now in a world where everything is being quantified and tracked. Okay, your social sentiment, your purchase histories, your geographic location, what products you buy, what products you look at on the web. Who are you connected to? What are your friends like? What do they do? Where do you travel? All these different things about you personally, but also about entities in the world, whether it's the weather, the climate, it's crops, it's vehicles, anything has a sensor on it. We're tracking all kinds of information. There's even a great paper on it was ostensibly a paper on Internet of Things, but it's about the Internet of connected cows. And so you can actually know when a cow is about ready to give birth or to give you good milk or whatever, anyway, through the sensor. So given all this data, the first thing you want to be is what you are naturally as a human, is curious and creative. So ever since we walked out, the first humans walked out, they started asking questions about our world. Okay, so we ask these questions: why is this? How is that? How did this happen? What will happen next? So we're constantly asking questions, and so that innate scientist in all of us is how humans learn. And so someone talked earlier today about making sure we have good definitions of the terminology we're using, and I like to use a definition for machine learning that says it's algorithms that learn from experience. Okay, so by experience, it's basically seeing how the world acts or behaves. So humans are naturally good at pattern, not only detection, but pattern recognition. That is knowing what something is based upon the pattern, okay? So whether you're running away from a charging animal or you're going after food in the olden days, or whether today you're looking for patterns that represent certain cancers or diseases. So excellent talk earlier today about using retinopathy, okay, retinal scans, okay, biomarkers in the blood vessels in your eye to detect diseases, and not just eye diseases, but other kinds of diseases you may have, like early onset Alzheimer's. Okay, so being able to look for biomarkers and recognize patterns is what we naturally do as humans. So we ask all these questions, and what do you think happens when you ask questions? You go out and collect more data to answer those questions. And of course, you collect those data to answer those questions, but then with those data, it leads to new questions. And those new questions will lead to more data collection to answer those, which leads to new questions, which leads to more data, which leads to, well, you get the idea. Okay, so that's how we ended up with big data. So if you do sort of the mathematics of that, the amount of data we have grows in proportion to the amount of data we currently have. And if you've ever taken a calculus course, you know exactly what that function is. That's an exponential growth curve, where the rate of change of the function is proportional to the function itself. Okay, so this is how we end up with big data, is this exponential growth in data because we're asking questions, because we're curious, because we're natural-born scientists. Of course, some of us live out the world of being a scientist. Not everyone in the world lives out that role, but they actually are innately a scientist. But I like to point out that the growth of data, which is exponential, has absolutely nothing to do with our real challenges. I mean, data storage, in my humble opinion, has nothing to do with big data. So I like to tell people big data is neither about big nor data. Okay? And by that, I mean the volume is irrelevant because we have storage capacity for whatever we collect. And I focus less on the data, but more on the value that we extract from all our information assets. So big data is about information extraction and exploitation from all of those assets that we collect. But so the real challenge is then now connecting, looking at all possible combinations of these things. So instead of having like a linear series of something, let's say you're trying to predict the outbreak of a disease, and all you have is a one-dimensional time series, the occurrence of this disease as a function of year or as a function of month or season. If you have a one-dimensional time series, there's all kinds of statistics books on time series forecasting that tells you how to predict a future value and a simple function, y is a function of x. Given x, predict y. We call that regression. The problem with regression is it ignores all the what we call exogenous factors, the external factors that influence that functional behavior. Okay, so you can predict that a certain thing may happen, for example, in the price of a financial market, and then all of a sudden it does something you didn't expect. Well, that's not too surprising because all those time series forecasting models use autoregressive techniques. That is, what I saw in the past is representative of what I'll see in the future. So something that's a tipping point or a chaos moment where it all of a sudden exponentially diverges from its prior behavior is completely not predictable in that kind of model. But what is predictable is that if you start including all the external factors, okay, of course impossible all, but a very large number of external factors, especially the explanatory factors that actually determine the behavior of a system, we can now understand why something suddenly deviates from prior history. Okay, the time series is now behaving in a different way. It's because it's affected by this world event or this price of something or this particular action a person took or this particular situation context that person or entity is experiencing right now. So that's the kind of richness of data that we are collecting now. We have very strong contextual information about people and things in the world, and we're going to have even more when we think about these sensors, which are giving us even more insights. Okay, by Internet of Things, we can now know, for example, temperature, weather. We can understand what you're buying, when you're buying it, where you're buying it, all kinds of contextual information. So it's the combinations of all these data pieces that's really the extreme growth curve on this plot here. So combinatorial growth is actually much worse, okay, than the exponential. Or another way to say it is 2 to the x, all right, is much more a stronger growth curve than x squared, but x to the x is even greater than all of the above. Okay, so x to the x is an approximation, a simplistic but pretty reasonable approximation of the factorial function. That is, how many combinations, if we have x number of things, or n things, there's n factorial ways we can look at them all. All right, so if there's 3 things, there's 3 factorial ways you can combine them. Then 3 factorial is 3 times 2 times 1, that's 6. If you add one more thing, that is 4. Okay, if you have 4 things, how many different ways can we combine 4 things? So this is the house party. Okay, this is the house party problem. How many different ways can I seat my guests? Okay, so if we have 4 guests, there's 4 factorial ways. 4 times 3 times 2 times 1, that's 24. What if I invite one more person? It's 5 factorial. That's 120. One more person, 6 factorial. It's 720. One more person. You've only gone from from originally 3 people where there's 6 combinations to 7 people, and now there's 5,000, 7 factorial, 5,000 combinations that you need to evaluate. Should I set this person next to that person? Should they be at a different table? That's too much for my brain to consider. All right, so why is this an issue? Again, if we have 3 data sources, there's 6 ways we can combine them to explore them, one at a time. There's 3 different ways you can do it one at a time. A, B, and C, all right? And there's 3 ways you can do 2 at a time, A and B, A and C, B and C. Did I repeat that? A and C. I don't know if I said that one. And then there's basically one way to look at all of them at a time, A, B, and C. Okay, so looking at all of these combinations is exponential. So let me give you an illustrative example of this, which is not about data, but I'll bring it back to the data science analogy in a second here. Okay, so let's say I have a step function. And I don't mean a step function in the math sense. A function that if I take n steps, I'll be a certain distance away from where I started. Okay, so as most humans, we walk linearly, right? So if I take 13 steps, I'll be 13 steps away from where I started. All right, so just making a rough estimate of that, 13 steps is about 8 meters. So if I have a linear step function, I take n steps, I'm essentially, okay, in English units, which I'm familiar with, it's 2n, that is, it's 26 feet from where I started, because that's about 2 feet. Okay, so that's about 8 meters. Okay, so that's so if our data is growing linearly, it's manageable. I mean, I can walk across the stage and come back in less than 30 seconds. So what if I have an exponential step function? Okay, so so again, coming back to the data analogy, after 13 months or 13 years or 13 weeks, whatever it is, it's 2 to the 13 as opposed to 2 times 13 more data. Okay, so if my step function basically 2 to the 13, I'm 2 to the 13 times further away than after 13 steps using this function. Okay, anyone ever see the movie Jumper? Okay, so this person must have had a great step function because he could just jump across the world anywhere, right? So if you don't know the movie, check it out. Okay, so if I have an exponential step function, after 13 steps, I'll be, okay, big steps, I'll be 2 to the 13 meters from where I started. So 2 to the 13 meters is 8 kilometers. So I could probably walk around the inner city of Brussels maybe 2 times. So 2 times walking around the inner city of Brussels with my exponential step function. Okay, it might take me longer than 30 seconds to do that. Okay, but 2 to the 13, 8,000 meters. So let's say the same thing if I have a combinatorial step function. All right, so after 13 steps, I'm 13 factorial meters away from where I started. So what is 13 factorial meters? All right, well, 2 to the 13 is 2 trips around Brussels, or inner city of Brussels. 13 factorial steps is 155 trips around the Earth. That's a big difference than going across the stage. When we think about linear data growth, completely trivial. Exponential data growth, everyone gets all upset about. And I think, even I could walk around Brussels in less than an afternoon. But I don't think any of us could walk around the globe 155 times, assuming there were land bridges. But what if you again, to show how powerfully or greatly this function grows, what if I now double the number? Okay, so from 13 to 26. No big deal. Doesn't sound like very much of a growth. Okay, so if I were to take 13 steps using the combinatorial step function, it would enable me to make 155 trips around the world. If I doubled the number of steps with that function, 26 steps, 26 factorial, the number of steps around the world, the number of trips around the world increases from 155 to 10 to the 19th power. Okay, that's the scariness of this number. And why is this relevant? I'll tell you why this is relevant. If you ever play with a deck of cards, if you just want to think of all the possible ways you can take out just the blacks or the red cards, you're left with 26 cards. How many different combinations of that is that? Well, it's actually 4 times 10 to the 26 combinations. Yeah, so if you think you're going to memorize the cards, think again. But the reality of this is I actually encountered this in real life. I had a student working with a data set. He was analyzing properties of galaxies. So thank you, Kirk, wherever you are, when you talked about the AstroHack. Thank you. I don't know if you realize, but when he showed the AstroHack logo that spelled out the words AstroHack, each one of those letters is a real galaxy. Okay, it's a real galaxy, and there's a website where you can write your name or anything else you want using galaxies. So check that out. It's a Galaxy Zoo product. So I had a student working on some galaxies. I gave him this data set. It was 3,000 rows and 26 columns. It was an Excel spreadsheet. Most conferences you go to, if you say you have an Excel spreadsheet, they laugh you out of the room. You're not talking big data. Get out of here. Okay, if we're talking about the word big meaning volume, you're correct. But I just got through saying big data is not about big. All right, it's about the value you extract from it. And the value we can extract out of that data is explore all the different combinations of galaxy properties. Now, okay, substitute the word galaxy for your use case. Customers, health patients, diseases, financial services, whatever it is you do, just you probably have 26 attributes, at least 26 features of the things you're studying, whether it's your patient or your customers or your clients. You have probably more than 13 things you're tracking for those things in your domain, right? So if you're a very successful company, you may have 3,000 clients, and let's say you have 26 attributes. Okay, let's go back to my galaxy question. So all of us have this kind of data, and we might consider it to be small data. But if you're, I had my student explore the combinations of these parameters to find interesting subspaces. By that I mean interesting parts of this 26-dimensional parameter space in which there might be clustering, there might be principal components, there might be correlations among the galaxy properties, there might be some associations in certain properties. Again, some of the things we might just try to do if we're doing disease exploration, if we're trying to do drug discovery, or we're trying to discover adverse drug interactions. All right? Think of all the drugs in the market in the world. There's probably more than 26 of them, I imagine. And if you're looking for all possible combinations of those drugs that might lead to an adverse interaction among your patients, that's 4 times 10 to the 26. Okay, that's a lot. So I had my student explore this, and I didn't tell him about the combinatorial growth rate here. So I left him in the dark a little bit. And I said, okay, let's start exploring these 3,000 galaxies, 26 parameters, to find if there's any structure in our data. So I said, the first thing I want you to do is just to look at all pairs of parameters, okay? So there's 26 times 25 divided by 2. Trust me, that's how many pairs there are, right? Once you pick the first one, there's 26 choices, then there's 25 choices for picking the second one, so 26 times 25. And it doesn't matter which order you select them, so divide by 2, right? So 26 times 25 divided by 2 is what? It's 13 times 25. Okay, so that's about 300 and something, 325. Okay, so I said, look at all possible pairwise combinations and see if there's any strong correlation in those pairs. So anyway, so this student came to me at the beginning of a semester wanting to do a project with me. So he did this, and he came back the next day, and he said, is that it? I'm done. Is this supposed to be a semester project? And I said, oh, that's great. Okay, why don't we look at all 3-way combinations? All right? So I said, there's going to be a few more of those than what you just did. But what we're going to do is not just sort of traditional sort of correlation analysis, since it's 3-dimensional now. Let's do some principal component analysis. And since he had taken my data mining course, he knew what PCA was, and he was a really good R programmer, so he knew about PCA, he knew how to do it in R, so there was really no learning curve for that aspect of it. So he said, okay, I'll start looking for structure, see if there's any principal components in 3-dimensional parameter space from this 26-dimensional data set, looking at all possible triples. Well, after about a week and a half, I got an email from him. He said, I'm still working on it. Is that okay? I said, oh yeah, no problem, it's okay. I realized there's a lot. So after a couple of weeks, he came back and presented his results, and he had lots of plots, and there wasn't a whole lot of discovery there. There were things that we already knew in the astronomy world, because astronomers had already explored a lot of these things. But it was good, he was getting the experience. So after he did that, and we talked about it for a while, I said, how would you like to try to explore all four-way combinations? And he said, yeah, this is kind of fun. Who knows what we might discover? Because I talked about the fact that, that humans are really good at visualization in 2 and 3 dimensions, but we're really bad at visualizing in 4 dimensions. So astronomers, historically, they plot their data and they try to see patterns there. Not too many astronomers have plotted in 4 dimensions yet. So I figured, hey, we might actually discover something no one's seen before. So he was really excited, motivated. He figured, hey, it took me a day to do one. The pairwise, it only took me a couple weeks to do the 3-way. It'll probably only take me a few more weeks to do the 4-way. Well, he started the 4-way, and a month later, he said, I think this is going to take a bit longer. After another month, he said, is it okay that I haven't met with you yet? Because I'm still working on it. I said, oh, no. He said, I assure you that my routine is still running. He set up a really nice loop to run actually, I think he set up an Amazon instance in the meantime, so he really self-taught a lot of good stuff here. And so after the semester got to its end, he said, I finally got it done. And he said, damn, there's a lot of 4-way combinations. And I said, how would you like to try the 5-way over the summer? He said, no, I don't think so. So then I brought this equation out in front of him. I said, that's a good thing, because if you were to do all possible combinations of these 26 variables I gave you, and if you had the world's fastest laptop that could do one PCA, one principal component calculation in 3, 4, 5, up to 26 dimensions, it could do, if your laptop could do one of those every nanosecond, if it could do that, which it won't, but if it could do that, you would need 10 to the 9 lifetimes of the universe to complete this project for me. So I think I'm satisfied with what you've accomplished. All right, so why am I telling you this story? The point is that this is the challenge we face. It's not the fact that data is growing, it's the number of combinations that are growing. And the number of combinations that we're facing is something that we already do in this thing we call our brain. So the goal is to try to replicate as much as possible what our brains do automatically, right? So I don't need to pull out my laptop or a supercomputer and spin up an Amazon instance every morning I get up to recognize my wife or my kids or my grandkids. All right, it's automatic. All right, I don't need to spin up an instance to know which way out of my bedroom. So let this be a lesson. Okay, so one of the things that's going to be part of this smart self-driving organization enterprise I'm going to get to in a minute here is it has to be stateful. It has to remember things. I mean, most algorithms, you run it through once and it forgets, right? It doesn't remember what you just did, all right? So you want it to remember so it doesn't replicate the same, not only repeat the same errors, but have to replicate the computation all over again. That's ridiculous, right? So you know you have to do certain things when you drive, so the self-driving car needs to have pre-computed scenarios. It can't go back to the cloud and do a computation every time a child runs in front of your car to decide, should I brake now or should I not? I think we should know instantly what we should do, and that's what we want to get to. All right, so that pathway, all those connections, that connecting the dots, if you will, that we call knowledge, that we call intelligence, that we call smarts, that's what we're trying to achieve from our data. And now that we have these sensors everywhere, it's not 26 sensors, it's much more than 26 sensors. So if we were to examine all possible combinations in order to be smart about our business, smart about our world, and smart about our self-driving car, it would be computationally impossible. Not just prohibitive, impossible. So one way we solve this problem is what I would call in the data science world near-field analytics. So near-field analytics means I need to care about the things that are immediately around me, right? I need to know about my bank account balance. I don't need to worry about your bank account balance, even though you're very close to me, right? So the things that I care about and that I'm making decisions on are based on things that are in my near field. Of course, that's a very common terminology in physics, so sort of near field dynamics. Okay, so behaviors of stars and planets are influenced by things that they're closer to than farther away from. So it's not necessarily nearness in space, but nearness in feature space. There's attributes, there's properties, there's context in which data matters in a decision, and other data do not matter in that decision. So first understanding context helps to reduce that combinatorial explosion, hopefully, to something manageable. So then we can achieve sort of this brain emulation in our data. So we're going from this big data world to smart data, and again, smart data is now connecting the dots, okay, whether it's through linked data, graph databases, or discovering links between our connections through machine learning, cognitive analytics, context, 360 view. All these ways are ways of achieving that connectivity, that connecting the neurons that lead to good decision making because you see the pattern, you've connected the dots. So someone once said that the essence of human intelligence is pattern recognition. That is, I see it and I know it. I see it again and I still know it. Okay, pattern recognition is what we're good at. The only way we learn to read is we recognize the pattern of letters and words in sentences. All right, we go through life as social beings and learning beings by adding to the body of knowledge and body of learning we already have. And we don't start from scratch, like I said, every single morning and have to pull out the supercomputer to recognize my wife, okay? So same thing with our data. If we can achieve these learnings, that is this knowledge graph, we can now make more sensible, I don't want to say rapid, that's a buzzy word, but more effective and efficient decision making from our data. Okay, so effective and efficient, I distinguish those. Efficient means in good time, in a timely manner I can make a decision, and it's effective because it's a meaningful decision. Not just any random decision, it's a meaningful decision. So that's why meaning-filled data, and I specifically misspell meaningful here, meaning-filled data comes from semantics, ontologies, taxonomies, these kind of formal ways of describing the content and context and use cases of our data, relationships to other things. But there's also crowdsourced tagging. Okay, what do the users say about this? What do the customers say about this? Okay, so how many of us go online and buy something and look at none of the reviews? I don't think many of us do that anymore, right? We usually look at the reviews. What are the reviews? The reviews are metadata about the product. The metadata crowdsource opinions and reviews of that product by other people, by people that we trust. And whether we trust them or not, it's a crowdsourced collection. So the ensemble average of that stuff and some mental model of ensemble averaging, you say, yeah, I'll go through with this or I won't go through with this. But not only, some of these things are explicit, then there's also the implicit tagging, implicit metadata, which are the breadcrumbs. And so by breadcrumbs, it's a phrase that's often used in web analytics. So when people travel through your website, you see what links they clicked on, what pages they went through, what things did they view. So that breadcrumb trail tells you something about user interest, user intent. It also tells you about whether or not your website is effectively designed. And we learned a lot about this at NASA when we were doing interfaces for data science, for data sets, I should say. And we discovered that people were sort of meandering through all kinds of web pages that we had, some of those indices I talked about at the beginning here. And we actually greatly and more efficiently enabled the scientific discovery of the data sets we had. Okay, and the way we discovered that is just by looking how people navigated our website. So breadcrumbs don't necessarily have to be just sort of web clicks, but in any way you have a user experiencing something, using something, trying out something, if you could track that behavior. Okay, so if you know about eye tracking software, where do people look when they look at a web page? All right, so eye tracking software is an example of this. What do people first look at when they land on your web page? What is it that's getting their attention? Is it the thing you want to get their attention? Okay, so using eye tracking software, people, in studies, because most of us don't just don't do that naturally. But if you volunteer for a survey and a study, they will, they put the goggles on and they'll see what you're looking at, and they can improve the experience from the user breadcrumbs. So user trails are another kind of metadata. And so think about just how people use your data in your organization, how your organization uses data, how individuals use data. those use cases and those uses of data, if you can capture that, and hopefully if you're in any kind of financial services or healthcare industry, you are tracking those uses because you have to approve compliance that only the right people are looking at your data and the other people are not looking at your data. So you want to have those kinds of user tracks. But they give you information about the, not only well, several things. They tell you about the usability, can people use it? They tell you about the usefulness, do people ever go there? But they also tell you about use cases. All right, so this is one thing that we talk about process mining in my company quite a bit because organizations are saying, how can I use data mining to improve our business process? And I said, well, if you can understand how people do their process, you might discover that they're doing something that takes 72 steps and they can reduce it to 13 or something like that. And this was a real example that we discovered. Because there was these signature and approval cycles that people had to go back and forth and back and forth and back and forth and back and forth to get approval for something. And I said, you really only need these approval steps here and there. And we basically cut like 80 or 70% of the steps of the process out, okay, by understanding how people moved through their process. So all this stuff becomes possible when you're able to quantify and track this stuff. And again, I'm not trying to say this in a privacy exposing mode. I appreciate all the talk today about data ethics, data privacy, and proper uses of data, but even in the proper use context, understanding user trails through the data enables you to be smart about your data and how it's being used, and to enable more smartness in your data. All right. So data-driven applications are going to become like the norm, okay? And they're probably already the norm for everyone in this room, but we discover when we talk with a lot of our clients that they want to get there, they don't know how to get there. So you probably saw that quote earlier this morning, how big data is like teenage sex. You saw that quote. Big data is like teenage sex, right? So everyone's talking about it, no one really knows how to do it, but they think everyone else is doing it, so they claim they're doing it, okay? But a lot of people don't know yet how to do a lot of this stuff. So we were in our own little filter bubble here. We all love this stuff. We're all doing this stuff, and we think everyone must want to do this. Everyone must be doing this, and of course everyone must be doing it correctly. That's the biggest fallacy in the room. We assume well everybody else is doing it correctly, so I have to be careful not to claim I'm doing something incorrectly. But anyway, so the Internet of Things will, again, because we're putting sensors on the world and we're connecting information about things. So it's not just I'm getting information about this car or this customer or this event. I see how it's similar to that other customer or this other car or this other event. So now I start making those connections. So now everything is interconnected in this crazy world we live in. So one thing we need to do to manage this data flood is, first of all, we want to do edge analytics. And by edge analytics, I mean moving the computation to the point of data collection. So this is one way to manage your data flood, right? So anyone in the room ever heard of compressed sensing? One hand goes up, maybe. So compressed sensing is when you measure something and then you essentially you store the description of the data, not necessarily the data. All right, so a simple example, imagine you have a time series of maybe the jet engine. Okay, so a typical airplane jet engine produces 30 terabytes an hour. All right, so if I'm flying back home tomorrow morning and that engine, it's an 8-hour flight, there's 2 engines on the plane. Okay, so we're talking already half a petabyte just on that one trip. Okay. So do you really need to store every bit and byte from that time series of that engine? What if you could you basically see the performance, which might be like the mean temperature or the mean RPM or the mean something, lots of different things you're measuring. The mean, the variance, maybe the skew. So you think about sort of traditional sort of statistical measures of that stream of data, and so you can basically take 50 million numbers and represent it by 5 or 6 numbers. But as soon as that mean deviates from where it has been, as soon as the variance suddenly changes, like this, usually high variance usually is a signal that the machine is going to break. It's also, believe it or not, web clicks on a website by your customers, high variance, a high frequency compared to their previous click history is usually a signal that you're going to lose that customer. There's a business that did this study. They commissioned a $1 million data science study to say, why are we losing customers? A very large corporation. They they figured out that web clicks was the answer. That is, there was a sudden increase in the intensity and number of visits to the site because they're maybe doing some price comparisons, they're shopping around, comparing with other businesses, and before you know it, they take their business somewhere else. So they implemented a little soft touch customer service. That is, they provided like a reach out to them. Hey, did you know we have this? Did you see this on our site? And they estimated in the first business quarter, implementing this soft touch response to this business click signal, high variance signal, they estimated in that first quarter they saved their business $1 billion. And that's with, one with 9 zeros after. That's a lot of dollars to save just counting web clicks. Okay, and so the signal there was not, or I should say that the data that really matters there is not every single web click that every single customer in that organization makes on their website. It's the change in the state. Okay, so there's a certain state that customer has, a certain variance of a certain frequency in which they visit, and all of a sudden the frequency, the variance of the data changed. So one way we can manage our big data flood from these sensors everywhere is we can sort of capture in a very few parameters, if it makes sense. I'm not saying all data streams are this way, but if it makes sense to capture a description of its behavior and to just store those few numbers. And a few might be 4 or might be 400, but it's better than 100 billion numbers. And once you identify this stream of numbers, or this data stream is represented by these few numbers, then the next time, so when I see a deviation from those numbers, that is the mean, the variance, or whatever, suddenly there's a very skewed distribution, for example, or what I like to talk about high kurtosis, okay? So kurtosis means all of a sudden there's a bimodal distribution. So now suddenly the system is not behaving in one mode, it now has 2 modes of behavior. That's not normal, okay? So even some very simple statistics that you could learn in grade school, like kurtosis and variance and standard deviation and mean, can become a good way of minimizing this data flood. So now you have these characteristics, and that's the important word. It's characterizations of the data stream. It's not, and so that's metadata. So the metadata again is data about your data. It's knowledge, information about your data. So given that metadata, now you can do intercomparisons with other data streams. So you now can sort of calm down a little bit with this factorial, combinatorial explosion that is computationally impossible to solve, and make it a completely solvable problem. Then you look in near field, that is, you only look at the things that matter both locally in real space, locally in time, locally in your feature space, in your customer space, or whatever, but also the way you represent the data stream can use this sort of compressed sensing type of methodology where you're basically capturing the essence of the data, not necessarily every bit in the data. And so now we can manage this combinatorial growth of data and achieve, smartness in our data and smartness in everything else we do. Okay, so if you actually made a slide, and this isn't that slide, but if you made a slide of every time someone says precision something or personalized something or smart something, you could probably fill like 100 slides like this. Smart cities, smart farms, precision medicine, precision agriculture, predictive maintenance, on and on and on and on. So it's taking over just about everywhere, right? So we're trying to achieve this place where we're smart about our data. Okay, we're seeing where it's going. We're predictive. We're personalizing it. That it's focused on exactly this particular context. I always call it the right decision at the right time in the right context, and it's personalized to that end user. Okay, so that's how we achieve our smartness in this crazy combinatorial exploring world. So this leads us to our smart enterprise, or what I like to call this self-driving enterprise. And I use this analogy again, sort of the self-driving car as our metaphor here, but it doesn't have to be a car. It can be your organization, it can be a drone, it can be a city, it can be even a deep space probe, and I'll have an example of that in a second here. Okay, so what does this thing do? Okay, so it might mean autonomous, but it doesn't necessarily need to be autonomous. It could be computer-assisted human or human-assisted computer. Either way, we want to get this sort of self-driving thing and sort of think about what it means. Okay, so I thought about this for a while, and I came up with sort of 3 categories of way of describing what is going on in such a self-driving enterprise. And again, using the self-driving car as my metaphor helped me to think about this. Okay, so we have these sort of defining characteristics of a self-driving thing. First of all, and most importantly, it's sensing its environment. Okay, there's streaming information coming in, and it's sensing information, right? So no driving is good with eyes closed. All right. So even a self-driving car, it has eyes on the road and has eyes on its surroundings. But so if you turned off all those sensors and you closed your eyes, I think it would be a very bad way to drive anywhere. So very first and foremost, any self-driving anything, organization, enterprise, drone, car, whatever, has to be sensing, and it's not just a one-time snapshot, it's streaming information, right? I don't just sort of look at the road up ahead, close my eyes, and then just drive. This would be a very bad idea. Okay. So it's sensing and streaming. It also has to be responsive. Okay, so it's not just collecting data, it's responding to what it sees. And then it learns from its experience. So far? Great, time is clicking. So it has to be learning from its environment. Okay, and it has to learn fast. Okay, so we talk about this as agile, right? We learn from our mistakes quickly, not after catastrophe. All right. So we heard the example this morning of a product that was delivered sort of 1 year after having the first conversation with the customer, and the customer says, "No, that's not what I meant." Okay. So having those iterative, fast, agile learnings, and we do that when we drive. We do micro adjustments all the time. So learning and agile, and of course, so if I'm driving to work, I already know the way to go, the best way to go, but it might change one day depending upon an accident or the weather or some other condition. So it also has to be optimizing and contextual, taking in other informations. All right, so again, the driving example is a good example. I know the shortest distance from where I am now to where I want to be. I can tell you that shortest distance, but that may not be the right way to go. Same thing is true in your business. You may think you're going to get from A to B in the shortest, most cost-effective, economical way, but maybe that's the wrong decision, because economical might be the wrong thing to do. All right, so you have to be contextual and optimizing, and of course the last thing is you have to actually be acting and doing something. So these 5 levels actually correspond more or less, and of course I sort of cheated. I knew this is where I was going in this presentation. And it sort of matches to the 5 levels of analytics maturity that we do in our analytics and data science projects. So descriptive, basically hindsight, what happened in the past. Diagnostic, which is what's going on right now, sort of real time, what's happening now. So that's oversight as opposed to hindsight. Predictive is foresight, seeing what's coming down the road. But you want to have a better outcome, and that comes from insight. And insight comes from all that contextual other data from all those sensors I was talking about. Contextual information comes from all these other places, all these other data streams. It's not just the one-dimensional, what's happening in front of my car right now, but I need to see, oh, someone's crossing the street or someone is turning. Okay, so that contextual information is now prescriptive. I can choose a better outcome based upon all those other sources. And of course, at the end of this stream, I act and decide in response to that. So I make the best decision, the best action at the right time, at the right moment, in the right place, in the right context. All right, so we're going from a very passive state to a reactive state to a proactive, okay, which is predictive, to the next state, which is predictive reactive. That is, I'm going to do something different, and in order to achieve an optimal outcome, and I can predict what will happen. Okay, so hopefully you're predicting well there. So hopefully your optimization is real, and that you're not going backwards. And so the organizational posture at the end of all this cycle is hopefully you're a sense-making organization, a smart, intelligent, self-driving organization. All right, so I want to skip a few slides because Philippe is going to throw me off the stage here. And I can make these slides available. There's a few more words here about the 5 levels of analytics maturity, which I more or less just gave to you, so I don't need to repeat that. And there's a little cartoon here. Here's the message in this cartoon. If anyone ever tells you prescriptive analytics is the same as predictive, they're completely wrong. Because predictive says given X, find Y, and prescriptive is given Y, find X. Okay, I had enough years of math to know that those are 2 exactly opposite sentences. Okay, given X, find Y, given Y, find X. So think about that. And so this metadata, which is data about your data, or other people's data about your data, or your data describing other people's data, all this contextual information enables your self-driving organization. So we're going from sensors to sense-making. I had a case study of the Mars rover. blah, blah, blah. Okay. The Mars rover is operating in a remote environment without human intervention. Oh, that sounds sort of autonomous to me. It's collecting data, taking samples with sensors. It uses algorithms to identify interesting things. We call those sentinels. Okay, the thing that alerts you when some army is about to attack your fort, that's the sentinel, right? So the sentinel just doesn't call out every 5 minutes, all clear, all clear, all clear. I mean, that could get pretty boring. They call out when something different, unusual, important is happening, and that's what we want to do. And then we make sense of all that and take actions. So we're going from sensors to sentinels to sense, the machine learning piece right in the middle there. This is all over the world, whether it's tsunami warnings or cybersecurity warnings or health alerts, whatever. This happens throughout our life, okay, and throughout your businesses and the organizations you live in. And so, closing slide, we want to achieve this better world, and I'm going to use a very big example to end my talk here, which are the 17 Sustainability Development Goals that you can find at the United Nations, and 180, 90, whatever plus countries of the world have signed on to these development goals pertaining to poverty and wealth and education, gender equality, clean energy, so on and so on. And for each one of these 17 goals, there's KPIs, key performance indicators. And the last time I checked, there's 229 KPIs associated with this. So KPIs are things you can measure. So we can use our Internet of Things to know the things that are knowable. And we're using our big data analytics, which is tracking and quantifying everything in our world, and do discovery through data science to achieve the good, better, and best from our world. So thank you very much.